So I want to talk a little bit more about friction. And you are going to think that I am overlapping the horse and cart problem, but I'm really not. I'm adding new material, and so please be sure to listen carefully so you don't miss it. All right, so friction is actually a very complicated phenomenon, and it's something that has been discussed a lot on my physics teacher listserv, with disagreements among teachers who have been teaching physics forever and people with PhDs in physics. So it's actually an extremely challenging phenomenon, but we're going to make it as simple as possible, and that we are only going to consider two types of friction, static and kinetic. And there's actually disagreement about whether there is more, and if there is, what is there. But we're going to keep it as simple as possible, static and kinetic. And the first thing that we did was we looked at easy examples, like a block sliding on a surface. And the idea is that if the force applied to a stationary or static box is greater than the maximum static friction, then the box will slide on the surface. And then if the force applied to a sliding box, so it's already moving, is greater than the kinetic friction, then the box continues to slide. So we looked at these two kind of easy examples. And then along with that, the simple view is that the force of friction is always opposite the direction of motion. So friction always slows down an object, okay? And so hopefully you realized that on the horse and cart problem, friction actually doesn't always act opposite the direction of motion if you think about like the whole object. And instead, what we want to think about is opposite the direction of motion of the surfaces of the object sliding past each other. So we've always, again, up to this point, you've been taught that friction slows things down or it opposes the motion, and we're going to see a little bit different view. So one of the things that we know, or that we saw with the horse and the buggy, is that we're going to look at example one, which is walking, just like the horse, that the net force has to be forward because that's the direction that you're moving, and there is no other horizontal force to push you forward. And so we can think about our free body diagram. So we have the force of gravity on the person by the earth, and then we have the force normal on the person, and I'm just going to say by the surface. And we know that these two are equal. So if the direction of velocity is that way, then the force of friction has to be this way, because, again, that's what's moving the person forward, is friction. And so here we have a case where friction is in the same direction as the motion of the object. And we want to look a little bit more closely at how does this happen. And so I want you to imagine that you are walking on ice just in normal shoes, or like not like even gym shoes with a really smooth bottom. What happens is you really can't walk. Like, you can't make a big stride. You can take kind of little shuffle steps, but you can't like walk like you're on the pavement. And so compare walking on ice with walking on the sidewalk. So on the sidewalk, you can do like a really good push off and have a stride that's, maybe 2 feet long, 2.5 feet long. But with walking on ice, like I said, pretty much the only thing that you can do is shuffle along. And on the sidewalk, you have a lot of friction, so that hopefully helps you realize friction is what moves you forward. On the ice, you don't have any any friction at all. And so that we can see in our force diagram. We have you are pushing back on the road, and the road, this is ice, okay? The ice is not pushing very far forward on you, and so that's why you can't really go very far forward. Whereas when you are just on the road, your force backwards on the road is equaled by the road pushing back on you or pushing you forward. Okay. So here's the part that's interesting. When you're walking and looking at friction, this is actually a static friction situation. If you think about it, you do not want your foot to slide, because if your foot slides, like on the ice, you can't walk forward. You're going to fall flat on your face. Remember, you're going to fall on your face because your foot is pushing backwards, and you will then fall forwards. So if your foot slides relative to the pavement, you cannot move. So again, I showed this diagram already, but I want to show it again now that we're thinking more about it. So if this is our foot, and we want to move forward, we actually want the foot and surface to not slide past each other. And that is remain static, because that's the only way you can push the rest of the object forward, is if your foot is stuck to the surface. Okay, if it slides, so if there's kinetic or sliding motion, then you won't go anywhere. So walking is a static friction situation. Okay, example 2 is rolling like a car tire. So this is actually a really similar situation. When you think about when you push on the wheel, it doesn't matter what you're pushing with, and the wheel turns, think about it. If I have sliding here, you're not going to go anywhere. It's like trying to drive on ice. You can't go anywhere. So rolling is also a static situation, okay? That you don't want the point where the tire is contacting the ground, you do not want those to slide past each other. Instead, you want the wheel, like here, to turn forward, and then there's a new pivot point. Okay, so I know this sounds weird, but both walking and rolling are actually static friction situations. Even though there's motion, and we think kinetic is motion friction. That's why I said sliding, or I've been emphasizing sliding this year, is that we have either static or sliding, and we don't want to slide when we're walking or rolling. Okay, a while ago, you guys completed a worksheet, and quite a few of you got these questions incorrect, and so I'm going to go through them. I'm sorry I don't have examples of incorrect work like I usually do. But I'm just going to go through them. So a hockey puck has a coefficient of kinetic friction, mu k is 0.1. If the puck feels a normal force of 5 newtons, what is the friction force? So I just want to be able to make sure that you guys know how to do these calculations. So force of friction is mu times the normal force. And so this is going to be 0.1 is mu. And my normal force is 5 newtons. And so my friction force is 0.5, and it is newtons. Okay, so that is the first one. Second one, as a museum curator pushes a statue across the museum floor, there is a friction force of 1470 newtons. So we know that the force of friction is 1470 newtons. We got force of, kinetic, or coefficient of kinetic friction is 0.57, and we want to know what is the normal force. Okay. So, again, my basic equation is force of friction is mu times the normal force. So I need to solve for the normal force. I'm going to divide both sides by mu. And so I'm going to end up with the force of friction over mu is equal to the normal force. And so I've got 1470 newtons divided by 0.57. Mu does not have a unit, so there's nothing to put down. And I get 25, I'm actually going to round this, 2580, nope, 80 newtons. That's how I'm going to round it. Is that the normal force? Okay, a box is pushed to the left with a force of 20 newtons but does not move. If the normal force on the box is 90 newtons, what is the coefficient of static friction? Assume that when the push on the box is slightly greater than 20 newtons, the box starts to move. So we're going to say that our force of friction max is equal to 20 newtons. And we know that normal force is equal to 90 newtons. And so we've got force of friction is equal to mu times the normal force. And we're looking for mu. So we are going to divide both sides by Fn in order to isolate the mu. So force of friction over normal force, it's 20 newtons divided by 90 newtons. Notice the newtons cancel out. And that is equal to 0.22 is my mu static. Okay, last one. Sled is pulled across the snow at constant speed velocity. That's weird, that looks like a typo. The pulling force is 40 newtons. So if the total normal force on the sled is 20 newtons, what is the coefficient of friction between the snow and the sled? Okay, so let's do a picture. So sled is got constant speed. So if my speed, constant speed, that means F net is equal to 0. And so if we think about a free body diagram, if I've got force, pull, let's say our velocity is this way, that means my force of friction is going to be this way. And so I know that these have to be equal if F net is equal to 0. So my force of friction is 40 newtons. And my normal force is 200 newtons. So force of friction is mu times the normal force. Divide both sides by Fn. And so I end up with force of friction over normal force is mu. And so 40 newtons divided by 200 newtons is equal to 0.20, and that's mu k because it's sliding.